molecule.
Yeah, great. Thanks a lot. And for all of you who are expecting to see Chris here, I'm sorry that you have to put up with me for the next half hour instead. But yeah, Chris unfortunately couldn't make it, so I get to have the nice opportunity to share with you some of our recent work that's almost finished now, after quite a couple of years of very sporadically working on it. The work on the treatment of ultra-long-range Rydberg molecules, including all relevant spin degrees of freedom. So yeah, this is work that has been that I've been doing with Chris. And along the way, I will take kind of a circuitous path to getting to this topic. And I'll show some results also that we worked on in Dresden, with mostly driven by Panos Kianakias and in collaboration with Jan Michael and Francis. So with this audience, I don't think there's much need to really introduce Rydberg molecules, especially after the other talks you've heard this week and talks you will continue to hear this week. So let me just very briefly say what we're all about. To form a long-range Rydberg molecule of the type we're considering, so one formed out of a Rydberg atom and a ground state atom, we need two ingredients. Of course, we need a Rydberg atom, and importantly, based on the typical spectrum of alkali Rydberg atoms, and really most Rydberg atoms, you get two distinct classes of molecules out of this. One's where the Rydberg atom is in a state with low angular momentum and therefore has a large quantum defect, or states which kind of combine all the properties of these highly degenerate high angular momentum states of the Rydberg electron. So that's one ingredient, the Rydberg atom. The other is simply the Fermi pseudopotential and the extension to P wave due to Aumont. These are the pseudopotentials that we use to describe the interaction of the Rydberg atom with the ground state atom. And just like with the Rydberg side, we get two different classes of molecule here. We also see for this high Eiles state, two new types of molecules forming out of these. The trilobites and butterfly molecules that you've certainly heard about, where basically the partial wave, this big L, is approximately a good quantum number and gives rise to two different types of molecules. So to give you a picture of what these look like for these quantum defect states, you see that the potential energy curves that come out of this combination of ingredients are quite flat on the overall energy scale, but have these rapid oscillations caused by the wiggles in the Rydberg electronic wave function. Whereas when you take all these states out of this degenerate manifold, these hybridize together and form a much deeper potential curve, which again wiggles a lot in as a reflection of the Rydberg electron, but with different properties due to this admixture of many different angular momentum states together. One of these, of course, being the fact that we get a very unique and very complicated electronic wave function out of this with all the different properties that this entails. Now, when you include now the P wave scattering due to the Aumont pseudopotential, the situation gets a bit more complicated because, as many of you know, the alkali atoms all have a P wave shape resonance. And this is denoted in this internuclear distance by this red bar here. Basically, here this scattering volume in the Fermi and Aumont pseudopotentials diverges, which causes these potential curves to really start to shoot down from the degenerate manifold. And due to level repulsion, as we kind of try and constrain this within a basis of electronic states, causes it to flatten out and hopefully give stable potential wells. And up here near this degenerate manifold, that's where these Rydberg molecules really live, these trilobites and butterflies. And this was all work really done all the way back in 2000, 2001 by Chris and Hossein and their colleagues, and as well Ilya Fabrikant and colleagues. And yeah, of course, you know the pictures by now, the trilobite molecules, the butterfly molecules. These highly polar molecules are kind of the reason why there's been a lot of interest in this topic, at least from the beginning, because these kilo-dipole moments are in principle very useful for different applications. Since that time, there's been a lot of progress. Again, many of you really know this, so I'll fly through and certainly not give an exhaustive list of all the experiments that have really been done in this area, but I just want to highlight that essentially all these initial predictions, trilobite molecules, low angular momentum molecules, butterfly molecules, polyatomic molecules have all been confirmed at a qualitative and really semi-quantitative level since these first days. They've been observed in many different species. You even heard about these negative molecules from Rosario's talk today and other molecular perturbers. at all different kinds of densities and in different situations, BECs, optical lattices, and so on. So this leaves us to wonder kind of what's left to do now, 20 years afterwards. Is there more that theory can do? And in this talk, I want to show you that there's a lot of work to still be done and work that we have done in making the theory more quantitative. Basically, as experiments can now really give us information about the vibrational states at a megahertz level, we need to really try and build up the theory so that we can do calculations to reflect this accuracy. And the two ways that I'll talk about are first contributions from higher partial wave scattering, so going beyond this Fermi and Lamont S&P wave. And this is really the work done in Dresden. And then that'll take us to the really quantitative theory predictions, including all possible degrees of freedom, spin degrees of freedom, different fine structure, hyperfine, et cetera. And importantly, theory calculations which are converged. And we'll come back to that in a bit. So first, let's talk about how one would include higher partial waves, because essentially everyone has only been concerned with S&P wave scattering in all experiments and nearly every theory paper until now. These have been understood to be the only relevant partial waves to this whole process. And there's good reason for that, because from the Wigner threshold law that higher scattering partial waves really drop off quickly as a function of energy. But it's good to sit down and really test this sometime. So we started doing this. You can find from this same Lamont paper that gives us this P wave term, higher partial quantum partial wave results. For example, this case for D wave scattering, similar terms for F wave scattering, and you can try and do the same types of calculations. Put these into a Rydberg basis, diagonalize, and create potential energy curves. But this quickly gets tedious. Calculating these matrix elements gets really challenging. And due to some difficulties, basically, with this ratio of the tangent of phase shifts divided by the electron semi-classical momentum, these pseudopotentials really start failing as you go close to small k, or as you go to larger nuclear distances. So this gets really difficult. So we thought we would take a much simpler approach, the typical physics approach of assuming a spherical tau of uniform density. But in our case, we want to really assume a spherical trilobite of uniform charge density. And the idea here is the following. You're all familiar with this typical trilobite pattern shown in this contour below. But when you really look at the Rydberg wave function kind of in a different light, you see that this purpose of mixing all these different degenerate levels together is really to try and maximize the electronic wave function right on top of this perturber. And you see that it's actually 100 times denser in this little black sphere around the perturber than it is out here in these wings that give us this typical trilobite shape. And this leads us to think that maybe a different way of describing these molecules is really to think about a charge sitting on top of the perturber, some fractional charge due to this extra electron density there, attracting the negative charge of the Rydberg atom left behind. So we decided just to try and do this calculation, basically integrating the scattered wave function, moving out from this perturber, subtracting away the charge or the wave function that would be there if there was no perturber. And if you do this, you get quite a nice formula then for this sort of effective charge that the Rydberg places on top of the ground state atom here in its orbit. And even though this was a very kind of hand-wavy, loosey-goosey calculation, you see in the end that this formula has some really nice features that make us think it probably makes sense. So on the one hand, you have a sort of normalization factor. That's basically the Rydberg atom's density of states. That looks good. And you have this factor in red, which is just the Wigner-Smith time delay. So it's just the derivative of the scattering phase shift. And this also makes sense. If you have a positive time delay, then this negative sign out front means that your electron is, if you have a positive time delay, your electron is, of course, sticking more to the perturber than it would otherwise. And this negative sign out front means that this gives you a negative charge there. And vice versa, if you have a negative time delay, the electron is kicked away more than it would be in free space. And this gives you an effective buildup of charge on the perturber. And so then we thought maybe a different picture is in mind. So Barry mentioned yesterday a sheepdog shepherding a bunch of atoms together into a Rydberg polaron in a dense gas. And that I think is also a way Chris has described it in the past. But we really want to think instead more about a chameleon. The Rydberg electron shoots out a blob of charge. It sticks to the ground state atom. And then you form really kind of like a heavy ion pair between these two. The real positive charge of the Rydberg core and this sort of dressed negative charge on top of the ground state atom. Now, the question is, does this actually make sense? Well, we also explored this just by taking this charge, going back to our sort of high school level physics to calculate the Coulomb potential just by integrating the Coulomb force as a function of their nuclear distance. And if you do this, you end up getting, again, a very reasonable looking formula. And actually, if you look back at the early days of Rydberg atom scattering, you see this exact same formula derived by Borden and Kazansky in the 80s. In a totally different approach, but in the same context of Rydberg atoms interacting with ground state atoms. You see this has a couple nice features. One thing is that it really lets you interpret the scattering phase shift of the Rydberg electron off of the ground state atom like a quantum defect, which kind of makes sense. You know, with quantum defects, you have small phase shifts that accumulate due to the short range non-Coulomb potentials around the core of the Rydberg atom. And here we have very similar physics. It's just now these are accumulating around a different center. But in the end, the effect on the Rydberg electron is still the same. The other advantage is that we see from this formula that now we've done kind of what we wanted to do. We have a formula derived under kind of very simplistic methods that should apply to all high partial waves. So from this, we can really get an idea of how important these contributions are. And this gives us really a new way of interpreting these potential energy curves, because now we can really see how this charge on the molecule or charge on this ground state atom changes as a function of distance, and how this basically carves out these potential energy curves. Now, not surprisingly, because of all the things we threw away in this calculation, we get just semi-classical potential curves without these wiggles that are important for molecule formation. But it still fits the form and the strength of these potentials perfectly. And yeah, basically because these phase shifts are energy dependent in a rather complicated way, of course, you have for the P wave resonance this shape here, and that's what leads to this very strong accumulation of charge as the butterfly passes through here. But because of this dependence and the dependence of the electron energy on distance, these don't look like your typical ion potential curve. So even though we're assuming that there's sort of this Coulomb attraction between this stressed ion charge and the positive ion, we don't get things that look Coulombic in the end. But we get what we wanted. We understand how to come up with a good approximation for these potential curves. And yeah, here again is just this point that taking the semi-classical electron energy, you see that this gives you an R dependence, and that means that basically your charge picks up an R dependence through the K dependence of your scattering phase shifts. And that's all well and good. But we were wondering really, you know, we've only looked at L equals 0 and L equals 1 so far. The whole goal was to look at higher partial waves. And it would really be nice if we could get Coulombic potentials. If we really want to take this ion pair picture seriously, it'd be nice if there could be a case where we see Coulomb-like molecular potentials. And fortunately, in this case, physics or nature, whatever, is very kind to us. Because if you just go and do the Born approximation for higher partial waves in a polarization potential like you have for neutral atoms, you see that actually all higher partial waves follow a k-squared dependence. So they're all proportional to k-squared with this proportionality constant depending on the polarizability and getting smaller with increasing L. And as you see, if you plug this into this equation that we have for the charge, take this derivative, cancel out the k's, you get a charge that accumulates on the ground state atom that's independent of k and therefore independent of R. So this means that actually all the trilobite and butterfly physics that we've been looking at for 20 years, well, some of us, is really the exception in these cases. And actually for all higher scattering partial waves, you get an effective Coulomb type interaction between the ground state atom and the Rydberg atom. And yeah, if you don't believe the Born approximation, then you can check out these exact calculations using a 2-electron model to confirm it. So here's the summary thing for including higher partial waves. You have your trilobite curve, butterfly curve, and then essentially for all higher partial waves, you have these Coulomb-like shapes. Now this one for L equals 2, we calculated using, well, many different ways you can calculate this to get really the quantum calculation out. In this case, we did both a direct integration over the polarization potential. We used this Omont generalization as well. And Panos also developed a generalized frame transformation method that is able to do all these higher L's sort of automatically. But the important thing is you see that, yeah, they all wiggle, of course. These will also wiggle if you do the full quantum calculation. But we now know the full structure of this problem. We know all the possible potential curves that come away from this degenerate manifold of the Rydberg atom for all high partial waves. And they're all Coulomb-like. Now, of course, we had to come up with some animals to describe this. So following the form, we've got dragonflies, fireflies for F-wave scattering, dragonflies for D-wave, of course, and of course, gadflies for G-wave scattering. But now, of course, an interesting question is if these are really Coulomb potential curves, then they should support Rydberg vibrational states. And that would be cool to see. Now, of course, if you look at this potential curve with all the wiggles, it doesn't quite work that well because these wiggles mess up the real Rydberg series that you want to get from a Coulomb potential. But there's a nice solution to this. Just increase the projection of the total angular momentum. As you do this, the wiggles go away. And finally, when you have a total projection of the angular momentum equal to 2, so equal to the big L, then you get potential curves that are essentially smooth. And as you can see, they agree almost perfectly with just this approximation of a Coulomb potential. And if you now compute the bound states in this, putting in some kind of hard wall here to reflect the quantum defects that we don't know, they use now vibrational quantum defects, you see that these vibrational states fit very well in a typical Rydberg formula. Now, again, for the vibrational levels, not the electronic levels. And what's kind of cool about this is because you're doing just this effective charge stressing, you don't have all the electrons sitting on top of the perturber, just actually a small fraction of it. These have a very small reduced Rydberg constant. Which grows in the typical way you'd expect from heavy ion pairs because of the reduced mass of the molecule is not the electron mass, but it gets truncated heavily by this dependence on the Rydberg principal quantum number. So in the end, you get really quite a small effective charge sitting on top of the ground state atom. And yeah, I'll skip this for now, but basically, if you want proof that these really follow quantum defect series, here it is. You can take a look later. Okay, so that means that we now understand how all higher partial waves affect these Rydberg molecules. At least we see that each one that we add introduces a new trilobite-like potential curve, which all are these Coulombic potentials and all really become small in the end, like we expected from the beginning. And what's reassuring is that when you include this calculation for other states, for example, here, this is looking at the Rydberg P state out here, which descends into this typical butterfly potential wells at shorter internuclear distances. And we see the effect due to D-wave scattering. On these potential curves, it's on the order of about 1% or so. So that means these terms are not so important for all the potential curves we've been interested in before. It's nice to see that we have new potentials available, new molecular states available, but it doesn't mess up too much our calculations elsewhere. Okay, so now finally we can come back to the title of the talk and look at really a spin-dependent Green's function approach. And the motivation for this is hopefully kind of clear from what I just said. All the key physics that we need to determine these molecular states comes from the electron atom phase shifts. And if you know these well, then you know the properties of these molecules well. Now, the problem is these are quite hard to calculate, and especially because you really need them very close to zero energy. So you need to know the scattering length of the electron atom system, and especially really the zero energy scattering length. And this is quite hard to converge. And there's a bunch of different values given in the literature for these things. And this really determines kind of the overall depth of the potential. So it's quite an important quantity to get. And also this P-wave shape resonance really flies through all our potential curves, causes a lot of problems or adventures. But its specific position where it comes through all the different potential curves, of course, depends sensitively on where the shape resonance is found. And this also is hard to calculate. And of course, doing a low energy scattering experiment with an electron scattering off of a ground state atom at a few milli-eV, this is tough to do. So how can we really be quantitative then about our Rydberg molecule calculations if we don't know these fundamental ingredients to a very high level? And just to give you a sense of how different calculations, different experiments give these values, they tend to vary for the atoms that we're looking at 10 to 20, 30% or so. And this is kind of hard. So the idea is maybe we turn this bug into a feature. And we can use Rydberg molecules to effectively measure this scattering phase information. So if we take, for our Rydberg molecule calculations, a set of input data, for example, quantum defects, like you heard from Barry yesterday, we can calculate, or sorry, experimentally, we can obtain these very accurately, put these into the calculation, put in a set of scattering phase shifts from a calculation or a measurement somewhere, put in the hyperfine structure of the ground state atom, put in other details, the fine structure of the Rydberg atom, which is, of course, buried in these quantum defects. If we put all this in, calculate Born-Oppenheimer potentials, do this with a good method, include all these different spin degrees of freedom, really match what the experiment is doing, then in principle, we should be able to take our calculated vibrational states, compare them to what's measured in the experiment, and make adjustments and go back through this process. And I think Johannes will probably say a bit more about how they do this too in his talk. But this is kind of the idea in practice. And if one does this, then really, in the end, you can get a nice set of scattering phase shifts out. But there's some problems that one encounters. First one is that it's simply not possible to really converge these calculations if you use these pseudo potentials. So this was first pointed out by Christian Fay and colleagues almost 10 years ago now, that due to this singular delta function potential, if you just start increasing the basis and adding more and more Rydberg manifolds in, your potential curves just keep changing. If you do this sort of symmetrically with one Rydberg manifold below, one above, two below, two above, then they tend to just get deeper. If you try and play around with different combinations, they just never stop shifting around. So this means it's quite difficult if you want to take this theory calculation and extract a good scattering length from this. It's difficult to really trust this because if you do the calculation differently, you would get a different scattering length out. And this is especially hard in systems with this p-wave divergence, because here you really need to put a lot of basis states in to basically renormalize this divergence that you get in the scattering volume. So you need to balance the fact that this means it doesn't converge with the fact that you need this just to get potential curves that make some sense. And basically the consequence of this is that, yeah, your phase shifts depend a lot on the model. So here's just one example from this frame transformation theory that Panos developed, which is sort of a precursor to the, or an alternative, let's say, to the Green's function theory that I'll tell you about in a couple minutes. And basically this gives a potential curve seen in blue here for a very simple assumption of the strontium phase shifts, basically taking just an effective range and just a constant scattering volume. And we can do this and calculate a bunch of vibrational states for a bunch of different ends. That's what's shown here in orange and purple. And compare this to the experiment done by Tom and Barry at Rice. And you see, of course, that, yeah, this can match the experiment really nicely if you fit certain values to the scattering length and to the p-wave shape resonance. But as you can see in this overlay over here, if you compare the purple and yellow dots, you can get essentially the exact same binding energies if you take a much simpler potential curve and just fit different values to these quantities. So in the end, any sort of statement that we've measured or obtained the scattering phase shifts from this type of calculation should be taken with a very big grain of salt, that this is just a reflection of what model you're using to do the calculation. And it's even hard, as you can see here, to really distinguish between different calculations from experiments, because it's not surprisingly, at least for strontium, because it doesn't have the shape resonance, the states are a little bit more straightforward to look at. They're surprisingly kind of insensitive to a lot of these details. So one solution to this problem is just to live with this and say, it's fine. We'll have phase shifts that depend on the model that we're using, and we can still do Rydberg molecule physics with this. But this is, of course, a little highly unsatisfactory. In particular, like you can see here in the solid curves, I've plotted effectively what comes out of our fitting of these. And in dots are calculations done quite a while ago by Klaus Bartschott and Hossein. And you see these really don't agree at all. So, I mean, it's quite an old theory. Maybe there's improvements that could be made there. But also, clearly, the experimental side, you should be careful with saying anything about what these phase shifts are based on this sort of comparison. Solution 2, though, which I like better, is just to use a better theory. That's what theorists can do. And so, yeah, one example is this generalized local frame transformation that we use to develop these. But the problem with this is not built to handle spin degrees of freedom yet. It has some advantages, like you can go to arbitrary partial waves and it converges. That's a big advantage. but you can't really put in spin degrees of freedom. And why is this important? Well, for strontium, it's not such a big deal, but for other alkali atoms, it's a huge problem, actually, because here you have tons of different spin degrees of freedom to worry about. So I stole these nice vector drawings from Chris to summarize a bit of what you have here. Of course, at the Rydberg atom, it's not so bad. You have just the fine structure coupling that couples the electron spin to its angular momentum to form a total J. But near the ground state atom, things really become complicated. Now you have hyperfine coupling of the ground state atom that couples its nuclear spin to its spin, the spin of its valence electron, to form total F. But of course, you should couple also the spin of the Rydberg electron with the spin of the perturber to create a total spin, S. It tells you if you have singular or triplet scattering. And once you have this S, you should, of course, couple this to the partial wave to get a total J, because you also have spin orbit splitting in the scattering interaction. And putting all these spins together leads to a lot of potential curves, where you have basically, instead of just a single P or a single D state, you have 4 of each of these due to fine structure, hyperfine, et cetera, bunching together. And this really is problematic also for these convergence questions, because now you have to worry about converging a lot of potential curves or coming up with a basis set that sort of effectively works for tons of different potentials together. And as you can see here, these 3 colors are 3 different choices of basis sets to try and converge this. And you see that especially in this butterfly region, they're just all over the place. So this is hardly even a qualitative theory at this level. And this is a big concern. So that's what we tried to answer with a fully spin-dependent Green's function approach. So this work is built on a lot of previous work, in particular work done by Kuskivadze, Chibisov, and Fabrikant, where they used a Green's function method and set it up in this Kirchhoff integral form that can also include this spin-orbit coupling of the scattering interaction, but they didn't put in hyperfine coupling or the Rydberg fine structure. There's also a similar approach that was developed by Chris with one of his PhD students at Hamilton, which was basically a Green's function approach, which didn't have any spin degrees of freedom. And there's also similar work done by Wyman in the audience to basically do the same thing, as far as I understand. But what has been missing until now is really a fully spin-dependent approach using Green's function methods. And that's what we have done. The physics of it, I will mostly skip because I had to prepare this a bit last minute. And I think you need a lot of time to figure out how to make these equations interesting to an audience. So I simply will not really show them. The basic idea is that you can set up a type of surface integral formula for the total wave function using the full Green's function of the Coulomb electron, including all these spins. And that's really what took a lot of effort to develop. But once you have this set up, then you can put in the wave function near the perturber, which can be expanded into these scattering partial waves, and form basically a determinantal equation out of this to extract the energies. And yeah, the details are all here. You all understand that. And you can check out our hopefully soon to be archive paper with a tentative 7 there for all the details later. But let me show you some results. That's the more interesting part. So here you see the region of the potential energy curves, really where you have these P states at large distances that adiabatically connect into these butterfly potential wells at short distances. And here on the left, this is for really the n equals 23 butterfly states that connect with 25p long-range states. And here on the right is the same range for these 16p states. And as you see, these are really the regions where we have the most trouble with this diagonalization calculation, where our calculations are really the least convergent. And now we can reproduce all the types of potential curves that are seen there. And this is especially nice because there's a lot of experiments already done for us to really try and benchmark these calculations and see how well they do and how one can really start to fit phase shifts to really agree with these different experiments that have been done in these areas. Just to show you again why this is important and why we now think that this is really a quantitative theory that hopefully we can all use now to really make this whole approach fully quantitative. Here in black is the Green's function result for just this lowest butterfly potential curve. And all these other curves here are showing different diagonalizations with different basis sets. And here in purple, this is one of the typical basis sets that a lot of people use when kind of fitting these phase shifts to the experiments. And in blue is another typical basis set. And you see these are really not close to the Green's function, and even worse, they kind of bracket it in. But if you put more and more basis states in, again, you just sort of float all over the place. But with the Green's function, you really don't have to worry about this anymore. And just to kind of wrap up here, we haven't yet gone in and really tried to do the hard work of calculating vibrational states and comparing these with experiments. Partly because we kind of know in advance that this won't work unless one goes and really tries to refit phase shifts again. Because if you put the wrong ingredient in, even if the recipe is good, it won't taste good in the end. And that's really the situation that we have here. But we can already make some statements or some guesses even about what this method will mean for the phase shifts that are currently in use. So here I'm comparing the different S wave, that's these two down here, and P wave, and especially these spin orbit split resonant P wave phase shifts from two different calculations. So the blue ones are ones originally calculated by Fabrikant and coworkers that were found in this comparison, this collaboration between Peter Schnellkert's group in Hamburg and some of Bau's in Stuttgart, really found to be inadequate at explaining what they observed in the experiments. And through this, they basically refit phase shifts to change, especially the position of the shape resonance, to really get agreement between their calculations and the experiment. And they claim that this is now a type of measurement or precision spectroscopy of the shape resonance. And this is all well and good. It really works very nicely to explain their experiments. But as we see, if we plug these phase shifts into the Green's function calculation, which again throws away all this uncertainty from the diagonalization, we see that there's a problem if you look at this butterfly regime. So here in the black, show the potential curves obtained using these new set of phase shifts with this modified shape resonance position. They look fine, but they're quite shallow. They go at deepest to about 40 gigahertz below this lowest P state. And these blue potential curves are using this original collection of Fabrikant phase shifts. Okay, they differ, that's not surprising. But if one now uses a different experiment that wasn't used to fit the theory calculation to fit these scattering phase shifts, namely these butterfly molecules that were observed in Kaiserslautern in 2016, well, one starts to see that there's hints of a problem. They observed a lot of butterfly molecules down here at about 40 to 50 gigahertz, where there just aren't potential curves if one uses these updated sets of phase shifts. So one doesn't even have to calculate vibrational states. You can see already that these will not work already. So you really have to go back to the drawing board and refit phase shifts to use this more accurate calculation to really get trustworthy values. And maybe those values will actually, in the end up swinging back a little bit more towards Fabrikant's original calculations, because you see there's, at least qualitatively, these potentials are really in the right region. Okay, that's the main punchline from our current results. So we have a method that really works well. It converges, it includes all relevant spin degrees of freedom, really except for the hyperfine splitting of the Rydberg atom, which is very, very tiny, and we could include that if needed. But yeah, we have this method, it works, and now it's very close to being ready to use to really start trying to see if one can really get quantitative phase shifts out of these calculations and really make Rydberg molecule theory quantitatively accurate. And just as a teaser, this also helps us explore the phase space of Rydberg molecules a bit more easily, because it's also an easier calculation to do at high N. For example, we can see interesting states forming where the hyperfine splitting of the ground state atom becomes comparable to the Rydberg energy splitting. And you see that this can turn some of these purely repulsive trilobite states due to singlet scattering at low N into sort of more standard trilobite molecules at higher N, just due to this mixing between singlet and triplets. And yeah, this is more information. Just if you want to make it more quantitative, one should include or think about including non-adiabatic coupling, or maybe even try and extend this to D-wave, even though we know that this is small, and we see also that non-adiabatic effects will typically be small, but you can check out more papers like this for more information. And that brings me to the conclusions. So in part one, we showed that partial wave scattering for all Ls can be included in long-range molecules, both through this sort of effective picture of a dressed ion pair and quantitatively through various methods. And this shows that all other partial waves lead to the same types of potential curves, these Coulomb-like potentials. And in part two, we talked about how quantitative calculations are now possible, hopefully within the end of the month, so I don't have to change the 7 to an 8. And thanks for your time and attention.
We have time for a couple questions.
So from a point of view of spectroscopy, what you discuss is the difference between an effective constant and an ab initio exact calculation. But often spectroscopies live extremely well with effective constant because they describe the result. So it's a bit of a philosophical question, or do I see that too much in the side of a spectroscopist?
I mean, that's definitely true, but of course, typically these different effective parameters that go into the calculations, people have to redo these for each new molecular state they look at, each new principal quantum number. So it's not very useful even as these, because if they depend on these things, you have to redo this calculation a lot. But the other point that is a bit more philosophical is a lot of these measurements have now been done, and with sort of the outcome being a claim of, now we've measured a scattering length, now we've measured a shape resonance position, which would be very useful things to measure. I think Georg has called these like low energy colliders or something, which I like quite a lot, that you can really, from these Rydberg molecule experiments, do like a low energy collision and get this information out. And this would be quite a nice outcome, but you have to have a good theory to be able to pull this off. And at that level, it's important beyond just fitting parameters to spectroscopy.
Thank you.
If you go back to something like strontium, the synthesis, what sort of experimentalities would you like on levels like the separations to make a really good thing and be able to discriminate between the components?
Yeah, that's a good question. That so I think probably it would be the case that, again, we need as many different n levels as possible, and probably also different angular momenta, because like I showed with the S state, there really wasn't enough difference in the potential curves in the end to really discriminate between these models. There was like different disagreement between some of the higher excited states, like you can see up here. So these sort of ones that really start to probe the interior of the potential. And in principle, if we look at those a bit better, this would also work. The problem that we encountered there actually is that we need really also a good idea or a closer estimate of what the phase shift should actually look like to really try and do this. And the ones that we have from this theory calculation are too far away from what they have to be based on the experiment. So this is just too big of an approximation to use as a starting point. And also this is too big of an approximation to use as a starting point. So there's also kind of a theoretical problem there of having a good model to try and fit. But from the experimental side, just more observations is always good, and especially ones that really try to probe the short range physics. That would be very useful.
Just in what you call these Rydberg vibrational series. So that's like ion pair states with an effective charge.
Exactly.
What is the effective charge, or how?
Very small. So that's this formula here that works very well to describe these states. So I forget the magnitude of this now, but it's on the order of a part per thousand or part per million of a full electron charge. So it is very small due to this n to the 6 in the denominator. But that's okay because these vibrational states are really fitting in between each electronic state of the Rydberg series. So in between all of our Rydberg electronic states, we fit in one of these potentials. So they, for this case, this is for n equals 30, you see their vibrational spacing would be on the order of 0.5 gigahertz or so. So this still gives you enough of a splitting to really think of observing these. The big thing I hid under the rug, though, is that we don't know the short range physics very well. So we kind of put this in as a quantum defect. And this, of course, would be the main place where these maybe would be very hard or impossible to observe if there's really too much short range physics here that causes them to decay immediately or form rubidium 2+ or whatever.
L, I mean, these are sort of, you say L is bigger than 1, but are they really elements? So can you?
So this is really the L, the scattering partial wave L. So are you wondering about like the rotational quantum number of the?
We're worried about the like orbital and momentum character of the Rydberg electrons for excitation. Like so.
Yes. Okay. In essence, yes, these are highly L mixed. These are really coming from this degenerate manifold. But this potential curve will intersect different quantum defects, things like the F state, the G state, and lots of groups. So Stuttgart and Kaiserslautern now are really pushing experiments to really excite Rydberg atoms to these F states. And actually, Herbegat had a preprint out last week where they form these trilobite molecules exactly through this process. Or you could look at a situation similar that you have in cesium, where you have a different atom where the S quantum defect is close to these. And then you just hope to drive this through that admixture.
All right, let's thank Matt again.